You said that there was one wrong that you had on here?
The issues that I remember are, for the sled problem, I forgot to list a mass. I updated the online draft of it, but some people just don't have a mass written there when they should. That is this one. This one doesn't list a mass when it needs one. Oh, also on this one, I just forgot to show how to solve for normal force. So I think those are the two main errors.
I'm pretty sure I saw for normal force. Normal force, isn't that just taking the force of gravity minus the force of friction? That's what I did.
Not the force of friction, it ends up being the y component of tension.
I got the same answer, I just subtracted the force of friction from it.
Yes, and that's because the force of friction, the y component of tension, and the x component of tension are all the same number.
Yeah.
I will talk about the one you asked about. I will do the flower plot. While I've got this up and while I'm thinking about it,
Yeah, I'm cool going with this one.
So,
what did we need a weight for?
a weight?
Yeah, I had it on here, it's 25 kilograms.
Well, that's the mass,
Yeah,
first of
mass.
all. You needed the mass to find the weight, because the force of gravity is one of the forces present. And I did ask for all of the forces, so that was one of them.
Mm-hmm.
But we also need the weight to help figure out normal force.
And the weight is just 245 newtons.
Yes. So, figuring out friction, I did through using net force x-axis equals 0. And we know that net force is 0 because we're not accelerating.
Yeah.
So, net force is also 0 in the y, but in the y-axis there's 3 things that add up to 0. Normal force up, gravity down, and also the y component of the rope up.
Which is just sine 45 equals the f of y over 100.
Yep. So there's 3 things here that have to add up to 0 in the y-axis. If this wasn't there, it would just be normal force and gravity canceling out, and that's, again, the general assumption is sitting still on a flat plane.
You don't have to do that. You don't have to do the y in there.
Yeah, sitting still on a flat plane, these two tend to cancel out. But there's an additional vertical force here, meaning that normal force doesn't have to work as hard because the rope is helping it. And this is where negative 245 plus 70.7 is where the 174.3 comes from. Therefore, normal force would be positive 174.3 up.
That's honestly basically what I did.
Okay.
So it would be, do we have to show it like that? Because I just put like f of n equals 245 minus 70.7, and then.
You don't have to show exactly the way that I do it. That said, I'm a little curious as to why you wound up subtracting gravity from friction, since they don't point in the same axis.
No, I took friction from gravity.
Why?
Why? I just took like the opposite. So like it was minus 245 and then positive 70.7, and I knew they had to cancel out to equal 0.
Friction and gravity have to cancel out to be 0.
Yeah.
Well,
And I just took
they point in different axes, so these two things technically never directly interact.
I don't know how to explain how. I just know that that's what you had to do to get the normal force, and so I just took it from it. That's my answer.
I mean, you did get the right number, but that's only because the friction and the y rope force happened to be the same number this time around.
Yeah, if they weren't, I couldn't.
Yeah.
Yeah.
So you did get the right number. I will just say, as a general frame of reference, only forces in the same axis directly interact, and only ones in the same axis should be directly added or subtracted from each other.
Gotcha.
So I'll just say that as the general rule. Now, you also asked about the
Flower pot, yeah, I was completely lost with your work. Like, I understand the stuff on the side, I understand like the one to the right with the X's, and then how you got 56.6, no clue.
All right, so similar to the tensions holding up a sign problem that we did in class, we've got multiple ropes here, and we're gonna kind of end up in a two equations, two unknowns scenario, because the two ropes are working together to accomplish the same task. Vertically, both of them work together to overcome gravity. Horizontally, their two X legs are going to cancel out because those are the only X forces present. So all the work over here was dividing things up into their component forms, X and Y. We don't have tensions, so they're really just formulas. And those formulas get plugged into these two axes in order to try to cut down on the number of unknowns, make it entirely about T1 and T2 directly. So in the x-axis, net force x-axis, we're gonna have the two X components of the two tensions, and they have to add up to 0, because the entire purpose of this entire assembly is to hold the flower pot still. And if it's not accelerating, net force has to be 0. So the two X legs add up to 0. Plug in those two X legs. We've got, I made this one negative because it points to the left. T1 cosine 60 plus T2 cosine 60 equals 0. Then down here, same basic process of plugging in the components that we just found, except now both of the Y legs point up and the weight of the pot points down.
This is when I multiplied that out, the sine 60 plus sine 60 plus 10 times negative 9.8, I did not get that.
Okay. So right now, this first part is just looking at all the Y forces that are there that must add up to 0. Does this feel all right?
Yeah.
Okay. Now the next line down is taking the Y components found over here and plugging them in for T1Y and T2Y. This part here is plugging in the gravity formula. So does this line feel okay?
Yeah, I understand that.
Okay. So now this and this are basically our two equations with two unknowns. They both have T1 and T2, and each one on their own we can't solve for a value, but we can combine them. So in order to do two equations, two unknowns, you have to take one of the two and solve it for one of them. So up here, get the two t's on two different sides. Say we solve for T2 by dividing both sides by cos 60. And something weird kind of happens there. I'm going to rewrite it in black ink.
Cos 60 over cos 16 is just 1?
Yeah. Now that only happens if they match. One we did in class last time, the angles weren't the same, so they didn't cancel out. But here, they just cancel out. And that tells us, whatever T2 is,
T1 is the same.
T1 is the same. So this is two equations, two unknowns. It's just the two unknowns are the same. So what I did here was, since T1 and T2 are the same, I just made them one variable. And I just did T in both places, just one united number. But I suppose to kind of show it in the more general form, I will leave them separate and do the two equations, two unknowns, plug the second equation in over here. So, we know that T2 is equal to T1, so I'm now going to rewrite this with two T1s in it instead. Getting there feel all right? Okay. these two terms are the same, and that means we can kind of distributive property them back together, or really just add them back together. Whereas this term doesn't have a t in it, I want to send it over to the other side.
98.
So next line would look something like 2 times t1 times sine 60 equal to 98.
And then you divide that by 2
Mm-hmm.
and divide it again by sine 60.
Yep, so if I do both of those at once, t1 is equal to 98 divided by 2 divided by sine 60. And that is where I got 56.6 newtons.
Okay. Alright, yeah, this is, okay. This is how work wasn't shown here, and I was just like, yo, where did he hit that?
Yeah, sorry, I ran out of paper.
No, that's okay. Now I get it. You added up them two, moved that over, okay.
And then whatever t1 is, we've proven that t2 is the same thing.
But if it wasn't, we would have to plug that back in.
Yeah, plug it back in here. So this is 2 equations, 2 unknowns. It's just funny because they're the same number. No, I think it's funny. How you feel?
I feel alright. I struggle with trying to get them started.
That's fair.
Once I get it started, though, I can look you figure it out. It's just where am I going to start from? That's where I struggle with.
Yeah, I would consider this a net force question because you've got a bunch of forces acting together on an object. You have to consider what they all add up together to. And in the greater genre of net force questions, I'd say the starting point should be examining like all the forces adding up together equal to either 0 if it's not accelerating or ma if it is accelerating, and splitting up all the forces into their components and proper axes. So x-axis forces and y-axis forces. That is what I would generally recommend as the starting point for a net force question. On the actual test, if you are stumped on where to start something, do please come up and ask. Granted, I can't always just tell you do this, but I can at least make sure you understand what is being asked of you.
Can you see if like our drawing's right? Because I feel like sometimes I like,
Yeah, I
Like-
did that with which drawing was the
especially
sled
with
one.
like the directions, sometimes I'm just like, ooh.
The sled one, I didn't draw my like tension rope being pulled at an angle, and
Right.
it kind of messed me up at first.
If you ask me a question that I can't outright tell you like that's right or that's wrong, I might just sit there for a sec and ponder what I can tell you. That said, if you're right, I'm happy. And when I'm happy, I smile.
Got it.
When I'm not smiling, I'm not
There's some.
I just really have a big tool.
Have you started grading yet?
I have graded about a third of them. I've got Wednesdays that I need to finish.
What's
and
the,
I
what's the
obviously have
lowest
days.
grade you got?
Well, I'm not going to tell, I'm not even going to anonymously tell you another person's score. I will say that the ones that have been not great so far have mostly been because questions were left pretty much blank.
Yeah, you just get points just for having something.
Yeah, if you leave it completely blank, there's nothing I can do. And if you leave like a 20-point question totally blank, no answer provided at all, that's just minus 20 points, and then we're all sad. As long as you write anything, even just an answer, that is more than 0 points. I tried to make that point clear. No one left anything totally blank. So no one's test score is 0. But some of them, like the ones that are lower than standard curve deviation were primarily mostly blank. Like they would leave answers, but maybe not fill in like work, like just write a number and leave it at that. Which, again, if you've got nothing, that's what to do. But it's always better to have something in the workspace, even if it's like a paragraph explaining to me what you do understand.
I have 3 hours.
Yes.
There won't be empty space in this entire thing.
Please and thank you.
Do you think you'd have to do a curve on it or no?
I don't usually do, well, sometimes I do a teeny tiny curve, which is to say that if your grade is a C or lower, I might add a few points, but I don't always need to do that. Usually the grades happen to be averaging at about a BC like they're meant to. If you got an A or a B, then no curve. And that's, like most people get around B, low B. Hold on, let me check the scores I've actually got in here. Yeah, I will say, of the ones I've graded so far, things are looking standard deviation wise good.
You can do number 8.
Yes.
Oh yeah, I was gonna ask that one too. That's the.
Yeah. I just don't like how he got to like that triangle. Like I get how he did it, but at the same time, watching
The thing about this triangle is, you should write it on your formula sheet.
You know, I haven't written on mine. I just don't understand. Like at first, I couldn't figure out how you got a triangle like that. But then I looked at it at like an angle,
Yeah.
because like it was at an angle, and I just said, okay, since that. So I drew a triangle from that top arrow, where the
Yeah.
A is. I've made that into a triangle now.
Yeah, this triangle is made up of these 3 vectors and not even tilted at all, just literally dragged over here into position.
Yeah. Okay. So this is where I was like, why did you use? So like, can I pull this up so I can draw on the board?
Yeah.
So I know this was like 60 degrees. 90.
Correct.
So I knew this was 30, but how can we use this angle, starting from there, to do like the whole thing?
Because the rule is, the angle between normal force and gravity is the same as the angle of the incline.
Okay.
That is the rule that took me a year to grasp as a physics major. And that's the official rule.
Let me write that down.
Wait, but could you technically use 60 and
Yes.
still get the right answers? Because it's like, you would
Yes,
just do like
absolutely.
cosine or whatever. Let's see, depending on what you want to see.
Yeah, if this is your known angle, that will work.
You said the angle between what?
The angle between normal force and gravity is the same as the angle of the incline. But yeah, doesn't like, if that's 30, this is 60, and you can work from this one's perspective, it would just flip what sine or cosine tell you. Because if that is your known angle, sine would tell you friction and cosine would tell you normal force. Here, that's opposite because literally what's opposite and what's adjacent has shifted.
And then I get confused, is gravity and like the force of friction positive?
Weird thing about triangles is that one leg doesn't really care about positive or negative for the other legs, because each leg is basically a different axis, and X doesn't care about positive or negative Y. So even though friction does always oppose motion, whether this is up or down doesn't matter, because frankly the same basic triangle would work if friction didn't exist. Like there's a similar triangle I could draw for a frictionless scenario,
So the force of gravity is positive, it's not negative?
Well, it's technically negative, but again, once you make it the hypotenuse of the triangle, the other legs don't really care
If it's
what
negative.
negative means for gravity.
I just do, when I did the sine 30 with the force of friction static over gravity, I did it over a negative.
What did you get from that?
Dang, I can't find my word.
It's okay.
I got negative 49 newtons.
Oh, okay. So it's the answer, but negative.
That's what I got, yeah.
And then I guess it doesn't.
And I just put that in the, but I made it positive in the mu equation.
Okay.
I don't know why I did that, but I did do that.
Hold on, I've written all over my work. So getting negative 49 isn't really a problem.
You just gotta make it a positive when you do the mu.
You just have to realize that negative means down instead of.
Yeah.
Yeah, and this formula in particular, I mentioned I usually recommend putting absolute values on the force of friction here, especially because this formula really doesn't care about direction, because again, it is bridging two different axes. And really, again, the whole triangle is bridging multiple axes. It's kind of like how when we're doing vector addition and we have to adding together weird vectors like this, and sometimes x is positive and sometimes x is negative, and your calculator doesn't always know to tell you that x is negative. Here it's kind of the inverse. We know that gravity is technically negative, but your calculator doesn't really care about that, and neither does the rest of the triangle. That is mostly important for the overall context of how things add together normally. So this is kind of a weird, fuzzy scenario. Let's see.
Thank you.
Did it answer the questions asked about this one?
Yeah, basically, I was just trying to the triangle situation, but you explained it with the angle between normal force and gravity is the same as the incline.
Yes.
That's why I was trying to figure out why you drew like that.
Yeah, that fact took me a second to grasp on my own as a physics major. What helped me be able to do that from memory was my teacher showing me what various extreme versions of this scenario look like.
I had to draw out that 60 degree to 90, that's how I had to do it to figure it out. I was like, wait, okay.
Yeah, my teacher showed me what happens on a really shallow slope, in which case, shallow incline, and also gravity, normal force aren't very far apart yet. Meanwhile, on a ridiculously steep incline,
There are a lot of triangle problems. I hate triangles.
this test has, hold please.
The triangles is where I always because with the triangle problems, there's always so many places you can start, depending on what you're solving for.
Yeah, like half of the questions on this involve a triangle somehow.
Yeah.
But if it helps, test 2 I don't think is gonna have any. Because we're moving on to weirder concepts like momentum, which only ever points in straight lines, rotation, waves,
Yeah.
oh, pressure, we do pressure.
My geometry teacher got arrested, so we never got to SOHCAHTOA, and I didn't learn this until I was in pre-calc. So sometimes you just get the short stick.
Yeah,
This physics is better than my old school. My old school was physics of 400 kids. It was impossible to learn.
Oh my god, no.
Yeah, I went to a really big school before here.
What school?
like
Oh,
400 people in the same room taking the class all at once.
It was a big movie auditorium like that next door, but for 500 students.
I've never seen that in high school.
It was a school. It was a school of 20,000 kids. So
It was a high tea.
no, it was a college. It was a college. It was a college. I took physics at another school. I had had to drop it because of my midterm. Like, all he did was a midterm, a final, and a quiz before the midterm and a quiz before the final. I bombed
Probably
my
because he
midterm.
couldn't grade like that much
I
stuff.
bombed my midterm so bad. And he was like, yeah, but there's no way you're saving this grade.
Yeah, I like working at a small school for several reasons. I don't want to think about having to grade 400 of anything.
Mhm.
Yeah.
That's probably why most.
Yeah, but he had like 4 TAs.
Yeah, one would have to.
Yeah, he had like 4 TAs, so they all helped him grade. Well, that wasn't even the only class. He taught like another time with the same amount of kids.
Okay, but if you've got TAs, why not give more assignments? One, so that the TAs have work to do, so that you can pay them, and two, so the students get more practice.
His practice was us going to class, and like he gave you like practice problems to do, but they were never graded. It was just like you do them, and he never went over them in class. It was just that like he would teach his lecture, and then that was that. You had to go to office hours, but his office hours are always during my practice time.
For us.
So yeah, it always kind of screwed me.
Yeah.
Yeah, I know the WebAssign system isn't perfect, but at least it's practice that creates
It-
itself.
it
You
gives
can
us
do
something.
infinitely.
And we can also come in here and ask you, like, I'm almost, I could never talk to him. I never got a chance to like be like, okay, I don't understand this, that, and that.
I want you to interrupt me in the middle of lecture, honestly, if you've got questions, because if something doesn't make sense while you're in the room with me, it's never gonna make sense when you're not in the room with me.
The problem is it makes sense when I'm with you, and then when I'm doing it on my own, it's like, where do I start kind of thing.
Alright.
Yep.
That is fair.
Could you do 7 and then 10?
Come on.
7, I really have no clue of how to like really start. Like that one, like, I left that one blank on my practice exam. I'm just
So for 7, we did one a lot like it in class, like literally the same drawing, the same masses. I don't think the views were the same, but
attention.
what's happening here is we got this set up, and the first thing we need to figure out is it gonna move?
I just know the acceleration is 0 because it said it's not moving.
Oh, right. Like on my
You're
answer
asking,
key,
like,
I
is it
know
gonna
it's not
move?
gonna move.
I don't believe it should move. The weight is not as heavy as the box.
That's what I couldn't prove that it wasn't moving, but I knew
I just
kind of just
say
in my
'cause-
head that 100 is more than 50, so obviously it's not gonna move.
Or is that simply it?
That's almost it. Yeah, the weight of box 2 is what's trying to make things move. So the weight of box 2 is what's trying to get things moving. What single force would try to prevent things from moving?
Tension.
So it's just friction, but since the force of gravity is
Affecting
we're missing the middleman kind of, because you're saying the weight is making the friction stronger, which is ultimately stopping that box from moving. Kind of.
Okay, hold on. Over here, this is the,
static.
yeah, these are the 2 X forces acting on box number 1. And if things are not moving, these 2 things must be canceling out. Meaning that for this system to remain in place, static friction must equal or exceed the tension in the rope. From box 2's perspective, tension is holding it up and gravity's pulling it down. And if it's not moving, tension must be equal to gravity. Meaning that this tension carries the same 50 into this axis. So for this system to not move, static friction has to be greater than or equal to 50 newtons. And this is basically kind of hinting at what you were saying before. The weight of the object, which is the 50 here, is kind of being transferred through the rope into box number 1, and friction is indirectly opposing the weight of box 2. If friction, not the weight of box 1, but friction is greater than the weight of box 2, nothing should move. And so the next thing to do is determine what is the force of friction acting on box 1. Formula for static friction is normal force times mu. We know what mu s is. It is the 0.55. So the question is, what should get plugged in for normal force on box 1? 100, very good. And to very quickly do y-axis analysis on box 1, from box 1's perspective, you've got normal force up, gravity down. They must add up to 0 because the box is not accelerating up or down. Therefore, the normal force on the box is 100. 100 goes here. And the force of static friction on the box is either less than or equal to 55 newtons. Its maximum value is 55. The static friction is kind of weird in that it has a certain maximum that it can be, and it only ever uses however much it needs to. So right now, my calculator might have a maximum static friction of 55, but it's not, right now it's currently got 0 static friction because nothing's trying to make it move. And it's gonna increase from 0 to 55 as I begin trying to move it.
So since the force of friction is greater than the tension, that's why I won't move.
Yep, the maximum possible value for the force of static friction is greater than the tension trying to pull the box. Therefore, the box won't move.
But if it was the opposite, then it would move. Say the tension is.
Right. If mu static was 45, the maximum value for force of static friction would be 45 newtons. That is less than the tension, it moves.
I guess. So basically the only thing there you have to do any math for is
The tension.
the friction.
Yes, you have to determine what the
Because-
maximum force of static friction holding it still would be and compare it to whatever force
Because
is driving the
since it's
reaction.
0, you can automatically assume, since T is technically the normal force of the box hanging, if that makes sense, it's pulling in the same direction as it would be if it was on flat ground. So you know that.
It's kind of serving like a normal
Right,
force.
so you know that has to be 50 if it's not moving, and then same with the gravity and the normal force of the other box.
Yep.
Can I ask a quick? Okay, so that equation right there, the F of y, like, well, on here it's the whatever, F2 equals T plus FG squared equals 0. Why? I'm not understanding why isn't the force of gravity like 98 because it's 100 times negative 9.8?
Note that for both of these boxes, the 100 and the 50 are weights because they're in units of newtons. These aren't masses, they are weights.
So if that was
in
100
newtons.
grams, it would be 98 newtons.
If it was 100 grams, it'd be
Or-
9,800 newtons. No, 980 newtons.
Okay, so that's why since you already basically calculated F, the G squared for us basically, or G2. Force of gravity, you calculate, like, it's already
Yeah,
calculated.
yeah,
for
these
us, 'cause
already
they-
are forces of gravity.
It's already calculated, okay.
And that's already m times g, because it's in newtons.
The more you see newtons, it's already calculated.
It's already a force.
Mhm.
Okay, that's how I got it, so T minus FG, so it's gotta be 50.
If they were masses, we'd have to find the weight. Since they are weights, we would use them to find mass if we needed it, but we didn't need it.
Do you have a problem like this with acceleration on the exam?
I'm double checking.
If you had an acceleration, then I wouldn't know where to go.
Well, we did one in class and also on homework that has acceleration. I have to be a little bit coy.
Yeah.
So let me say it like this. The version of this question with acceleration takes a lot of time and a lot of lines of algebra. When I'm writing my test questions, I don't write them with the intent of them taking a lot of time and having a
Agreed.
lot of algebra. because like each question is meant to be something you can do in like 7 to 10 minutes, intuitively.
So basically, you want quick problems, and that's not a quick problem, so answer that for yourself.
I always make the practice test longer and more difficult
Than the actual.
than the
Yeah,
actual test.
the homework's harder than, the practice test is
Yeah, the
pretty rough, the
homeworks
homework's just
are-
really hard.
Yeah, the homework, one, was written by textbook people, and two, is meant to be something you can do with friends from the comfort of your dorm room, starting or stopping, and then taking naps in between.
Yeah, the homeworks, I do not enjoy those.
That is fair. I will take that under advisement as I revise future assignments.
But I do like how we don't have to finish them until finals.
Yeah.
Yeah, that is.
And I like the multiple attempts. So it's like, it balances out the pros
Yeah.
and cons. It's like, it's harder, but you
Right.
get all of the benefits. So.
It's entirely meant to be cheap practice, and you could still technically get an A in the course if you never do them. I just wouldn't recommend it, because you'd have to ace everything else.
And I just do it because like it helps you understand where you're at.
Also doing them helps your midterm grade, because I do factor in your chapter 1 through 5 homeworks and quizzes on that.
And then that's November 11th or something like that. Right?
Midterm, is it?
Midterm is the one that's about to happen.
It's like the Friday the 13th one?
Ominous.
October, yeah.
I remember. The last one will just be number 10.
Oh, yeah.
That's just a long one.
Dang, I erased the work for that one. So, here we are dropping something from high up. It's going to bounce off of the ground, and I worked this analyzing the energy that it has at each moment in that process. You could do part of this, someone asked me about this, so I'm just going to tell everyone. You could do this, at least most of it, without caring about energy. The first part and the second part, you could actually do with the old-fashioned first couple formulas, since it's just an object accelerating as it falls a distance. I worked it here with energy to show how that works, but you could do A and potentially C using those old ones.
I
So
like
we
the
can just
energy.
use the acceleration equals.
Well, what's the acceleration of a falling object?
9.8.
Exactly. Now, what I did here, and I'm going to rewrite it on the board to kind of expand it a little bit. Each part of this question compares two different stages of the ball's journey. So each part, A, B, and C, has a different before and a different after. And for all of those befores and afters, total energy initial must equal total energy final. And that means whatever forms of energy you have must add up to the total of all forms of energy that exist in whatever final state you're analyzing, even if the types of energy don't match from start to finish. For example,
Wait. I didn't really understand what you just said.
okay, so the law of conservation of energy says total energy, however much energy a system has before something
It's
happens,
gonna have when it ends.
yeah, the same total amount of energy will exist after the thing happens. And what that means is whatever forms of energy it may or may not have initially must add up to the total of whatever forms of energy you may or may not have afterwards. The types of energy are going to change, and not all types are going to exist at every stage. This is like the most broadest general form I could write, and frankly, you could write this on your formula sheet if you wanted to. And each part, A, B, and C, is about different befores versus different afters, and different forms of energy existing at different points.
So wait. GPEI is general potential energy.
gravitational potential
Gravitational.
energy initial.
Plus kinetic energy plus, I forgot what the E was again.
Elastic.
Elastic, okay. Kinetic energy plus E, elastic, gravitational.
And in part A, the first 2 points in time we are comparing, our first initial state versus final state. We are comparing an initial state of holding the ball 10 meters in the air, like on the top of a building, just holding it still in our hands.
And that's GPE.
Exactly. At that stage, it would have GPE because it's got a height of 10 meters above the ground. But if we're holding it still, it's not going to have any KE, and it's also not going to have any EPE because it's not being compressed, it just exists. So initially, all it would have in this stage is GPE. The KE initial term is 0, and the EPE initial term is 0.
So QPE just equals 1/2 mass times velocity.
That's the KE formula. Oh, sorry, no. I see what you're saying.
Yeah, I said GPE equals that.
Yes, you're right. So that's the initial state. The final state, we're gonna drop the ball, it's gonna accelerate all the way down, and we're gonna freeze time at the point where its height is 0, it's moving at top speed, it's like just barely touching the ground, but the collision stage hasn't happened yet. We're still at max speed before impact. I tend to pause time at that second a lot. So that is our final state. What forms of energy exist in this final state?
Isn't the velocity 0?
No, because the collision hasn't begun yet. We've paused time
So
at
the
the
velocity is
moment.
actually the highest it can actually be.
Correct. It's always the highest right before impact with the floor.
Okay.
And that's where we froze time.
So you asking what types of energy are at that point?
Yes.
Isn't gravity acting on it at that point?
Yes,
So-
but its current height is 0.
So GPE should be 0 then.
Exactly. At this point, however much initial GPE we had has drained away and entirely turned into kinetic energy. And because the collision hasn't started and the ball isn't squished, there's no EPE
So,
either.
for that, just GPE equals K.
Yep.
GPEI equals KEF.
And for space reasons, that's what I put on the answer key. But does the version on the board help show the energy forms?
Yeah, your drawing helped me because now I know that since it didn't like squish, like it's impacted but not fully impacted, that's why it's 0.
Yeah, it's, I apologize for any conceptual weirdness with this, but we have frozen time like the last possible moment before impact with the ground. We are at height of 0, but the collision stage hasn't started yet. So this is like, basically, okay, I watched a lot of Looney Tunes growing up, so I keep referencing this. This is the moment where Wile sees the anvil frozen above him, he says help, and then crush.
So for C, where it's like what height will the ball bounce to, and if there's no friction and all of the energy is conserved, will it always bounce to the height it was dropped from?
Yep. As long as all energy is maintained, we've stored the same amount of energy the entire time. As it bounces back up, it's just gonna regain all the GPE it originally had at the same height it started at.
Okay.
But that's again in a perfect world where friction doesn't exist and where all collisions are perfectly elastic, and that doesn't actually happen.
So, oh, sorry.
Yeah, you can go.
So say if like in C there was friction, how would we account for that?
If there was like air friction, we could figure out, say, how much work friction does, because air friction would just be a force that would act the entire time, and we know the distance it falls. work equals force times distance, so work would equal force of friction times the distance the ball moves through the air. That would be one way to account for it.
Mhm.
Now that said, calculating air resistance is a huge pain,
Okay.
because it involves not only the object's speed, but also its shape.
Oh,
So I would never ask you to calculate air resistance from scratch
Okay.
around here. Frankly, I don't even know the formulas to do it off the top of my head because of all the things that affect it. Usually in physics, you either assume I'm moving too slow for it to matter, or I'm moving so fast that now I have to do a bunch of headache calculus.
okay.
So where it's like, part A, part B, part C, they all start with the sum of energy initial equals the sum of energy friction, and
Energy final,
energy
not
final,
friction,
I'm sorry,
final.
energy final.
It's the same letter, I'm sorry.
But underneath, for every part A, B, and C, that's those are all different.
Yeah, each part is comparing to different points in time.
How do you know which ones to use though at each part? That's where I'm like, cause if I can get to that point, I can figure out
Because
all
yeah,
that.
at that point, it's just plug and play with that formula over there.
Right, and for each part, it's worth asking yourself, which moments am I comparing and which types of energy exist in each moment? So for part B, for example, here it says, assuming total energy conservation, what is the spring constant of the basketball if it compressed a certain distance upon impact with the ground? So that is that's changing the final moment now. We're now looking at, that's changing the final. Now, the final moment we're examining,
Doesn't last.
exactly, in this new final moment, where we've gone through with the floor collision, we've unpaused time long enough for the ball to fully pancake.
And now that ball's velocity is zero, making kinetic energy zero, meaning KEI,
Exactly.
which was, okay.
So,
Making it zeros, you're saying?
yes,
It's
in
not
this
like-
moment where we are fully pancaked on the floor, you stop for a second.
Yeah.
And you kind of have to stop because in bouncing off of the floor, your velocity reverses. Like it literally just switches
So
direction.
you have to pass zero at some point.
Exactly. You have to pass zero if you're going from a negative number to a positive number. And this is the moment where it hits zero on its way there. Kind of basically the opposite of hitting zero on the way up. Or really physically the same thing, just oppositely oriented.
But also in that question, it asks for the spring constant, and that's only in the elastic potential, and it's only in K. So you can use like the question to sort of like narrow it down what you're looking for too.
But if the velocity is zero when it gets to that point, how come you plugged in the velocity from part A into that velocity?
That's because I have changed my initial state versus the final state. For part B, my new initial state is the final state from part A. So the points that I'm choosing to compare here, I am now comparing this moment to this moment.
Okay.
And in this moment, you've got a bunch of KE. In this moment, all the KE is gone and turned into EPE. But your GPE didn't change between these two positions because you're still on the ground. You're still at height zero.
So basically with each step, we're using the previous one to solve the next one.
Yeah, that's how I choose to look at it, kind of advancing through time, one still frame at a time, or one key moment at a time. And you could technically do this one by comparing the very first step to this new final step. Mathematically, that would work out to be the same thing. So you could compare the real initial to this new final if you wanted to, and it would work out the same. There's usually more than one right way to get the right answer around here.
24, okay, so that's the difference. The 0.2, is that just, that's the mass.
Correct, that's 200 grams converted to
The
kilograms.
0.06 is just the difference of 24 minus 18.
Exactly. So that's a difference of 6 centimeters converted into 0.06 meters.
Because that's the sum of
And then you just solve the K.
Is that newtons per meter?
That is newtons per meter,
Okay.
and it's a very big number, because it would take a lot of force to make a basketball 1 meter longer. It would pop before that happened.
So how can we use the sum of that plus? Wait, no, that's K. Never mind, I'm sorry. Kinetic.
And then you're just going basically, for C, you're just going back.
Yep. Part C is comparing any point to a new final point where it rises all the way back up. And again, if you lose literally no energy, you should rise to the same height. But realistically, you're going to lose energy to air friction, and you even lose energy on impact with the floor. Even the bounciest ball you can get out of a grocery store gumball machine loses some energy on impact with the floor. And that's actually what we're going to be beginning to study next week. Chapter 6 is going to be about momentum and collisions. So this is kind of a
The only thing
preview to that.
The only thing I gotta remember is, like for B, I wanted to change velocity to 0. I wanted to change the V variable to 0, and I have to remember to keep it at 14.
I mean, well, there's one stage where the V is technically 0,
Right.
and that's this part. But for
That's
this,
probably-
again, this is always a before state compared to an after state. And again, that's going to be a very common theme for the next couple of weeks.
Where I'm showing is just like the second part of the A, B, and C. That's where I just gotta figure out. Like how you went from GPE initial, KEF on part A, and then kinetic energy initial with the.
I would just say, like, just kind of memorize that GPE is when it still has height left to fall. Kinetic energy is when it's moving, and then elastic is when it's compressed.
Gotcha.
Yeah, that's the way I do it. I just remember those three things. And
Yeah, for each form of energy, remember when it exists. Remember what scenario must be met for that type of energy to exist.
So the elastic is when it's compressed,
Or extended, but yes.
and then the gravitational potential energy is when it's falling.
When it has some distance, it can fall, yes.
When the height's not 0.
When the height is not 0 from your frame of reference, correct. And then KE is just, is it moving? Does it have a current non-zero velocity? How you guys feel?
nervous.
I'm nervous.
That's fair. I will point out, of the ones I've graded so far, everything's looking fine, looking good, like where I expect and want the average to be. I'm trying to say that as a comfort.
Yeah. Just don't have a very like strong math foundation.
That's fair.
So it always like just piles up obviously, and so then I feel like I just go in with a pessimistic outlook because
And this is so frustrating because it's more frustrating because you know exactly what it's going to do. You just don't know the value. I mean, it's physics.
Yeah, you
understand
guys know
what's
what
gonna happen.
should happen here, you just might not be able to do the math.
Right.
And
You
that is
understand.
why, I will point out again, if you are blanking on the math, I will give you points for a written answer where you describe what you understand. I might be looking for math, you might only get full credit for math, but I will give you points for you demonstrating what you do understand.
Like if you just write a paragraph, the ball will fall, compress, and then be shot back up at a certain distance.
Yeah, and then maybe including what you know about the forms of energy at any
Right.
given point. Like, if it's bouncing and compresses, it must have EPE during that stage, et cetera, et cetera. Any information you can summarize somehow earns you points. Even if it's not all
will you have extra sheets of paper to do the work on?
of them. Yep, that's this entire stack.
Okay, cool.
My stapler might not exist, but that pile is there.
That's good. Okay. Well,
I just struggle on starting. That's it. If once I can get it started, I'm good. Like I can figure it out. It's just I struggle where to start.
algebra once you get started.
on it.
If you are stumped on a start point, for one, ask me. Like, I wanna make sure you understand what is being asked of you. And two, sometimes it helps to just start writing down formulas and numbers. Cause if you try something and it doesn't work, why didn't it work? What makes more sense?
Like on my formula sheet, like I have all the formulas, but then I also write next to them like when you use them and why you should use them, because like
Good idea.
having just a formula doesn't really help me, but I gotta understand what
Yeah.
that formula means basically.
I think of the formulas as tools, and each question is a different thing you have to fix. Some situations require a hammer, and honestly, most hammers usually have something written on them about what type of hammer it is and what its like maximum force yield is. So label your tools.
Yeah. Or like another place that maybe I like write down all the variables that I know and then try and like match a equation.
First thing I
to
always
it.
I give you points for that.
Yeah.
I always draw.
Write your
It's the first thing I
variables,
do.
write your
Yeah.
formulas,
And
your
draw
points.
pictures. Yeah. I have little stick figures and like an actual like I do all that.
The drawings always help me first too. That's
Mhm.
always like if it's
The
the
only-
drawing ones.
Only thing about the drawing is, I know there's a car one on there, and the wording was really weird, and I drew it. I don't even know how I drew it, but it was the simplest question, it was like just 36 seconds, you know which one I'm talking about?
Was
The
it
point-
number 6?
It was the .01 hours, but it confused me where it said, the slower car is behind the faster car, how long will it take the second car to catch up? And I was like, how is that possible?
If the slower
If the slower
car,
car's behind the faster car.
Yeah, wouldn't it like never catch up?
It would never catch up.
whoops.
That's, so I drew that, and I was like,
Yeah, but you had told us in class
Yeah, it's-
Wednesday to ignore it.
right.
Yeah, one, relative velocity isn't there. Two, I missed that when I was making my answer key. Whoops.
That's that's the simplest problem. I just drew it and I was like, what?
Wait a minute. Okay, yeah, so it turns out your answer was better than mine. I make mistakes sometimes. Please call me out on that. You guys need anything else for right now?
No, food. I'm
Food
gonna
is
go
important.
eat.
Do not take a test on an empty stomach.
Yep.
Have a nice day. Get a snack.
Thank you.
Thanks.
I've always had a question I've always wanted